Today's the day. We are doing a Vesper mega video. I'm going to draw 36 Lewis structures, 36 3D structures to complement them, and figure out the Vesper notation, the molecule shape, whether or not it's polar, and what the strongest intermolecular force is between the molecules, all based on a Lewis structure. 36 of them, let's get started. CH4. Carbon brings 4 electrons and each hydrogen brings 1. That's 8 total. So I draw my central atom carbon, I draw my outer atoms, and I put a bonding pair of electrons between each set of atoms. That's 8 electrons. I'm done. The Lewis structure is this. Now this carbon is the central atom and it has 4 atoms bonded to it. That makes it AX4. There are no lone pairs, so it's E0. We don't usually write E0. It's just AX4. That means it is a tetrahedral molecule. And now that I know it's tetrahedral, I can draw the 3D structure. I'm going to draw a hydrogen on top. I'm going to draw a hydrogen coming out this way. This should be a 109.5 degree angle. One hydrogen coming out at you, and one hydrogen going back into the page like that. It's kind of like a little tripod with a hydrogen sticking out the top. That's the 4 of them. And again, the bond angles are 109.5. Is it polar? Because it is perfectly symmetrical from all vantage points, and more specifically because carbon-hydrogen bonds are not polar in the first place, this molecule is not polar. And if it's not polar, I guarantee you the strongest intermolecular force is called London dispersion forces. Fat chance I'm writing that out every time. I'm going to call them LDFs. Cool? Cool. We're going to do this again for CF4. Fluorine brings 7 electrons each, so this molecule is going to look pretty similar, except my fluorines need full octets. I'm going to put my F here, fill those with electrons. If each F brings 7 and the carbon brings 4, that's 32 electrons total. So here's 8, 16, 24, 32. I'm done. This one is also AX4 and is also tetrahedral. And so it's going to look exactly the same when I draw the 3D structure. Here's that F, here's that F, here's that F, and here's an F sticking up out the top. Done. Is it polar? Well, CF bonds are polar because their electronegativities are pretty far away from each other. I think C is 2.4, 2.2, and F is 4. So they're almost even, you could classify them as ionic bonds, but we don't. They're covalent. But they're all pulling on carbon equally. It's symmetrical from all directions. So even though the bonds are polar, the molecule is not, and the largest, strongest intermolecular force between them all are London dispersion forces again. Boy, that's 2 LDFs in a row. Maybe this one will be different. Here we have CH2F2. We have carbon connected to 2 hydrogens, just like we did before, and connected to 2 fluorines, just like we did before. I can guarantee you this is the Lewis structure. It is AX4 again, because you have a carbon in the center connected to 4 atoms and no lone pairs on the carbon. It is tetrahedral again, because it's AX4, and so we can draw it out this way too. I'm going to put my hydrogen on top. It does not matter where you put these. Like, I could have put my F up here, my H down there. The only time it would actually matter is if you had 4 different things connected to carbon, and that RS and enantiomer stuff has nothing to do with Vesper, so don't worry about it. But this molecule is not symmetrical from all directions like these were. If I divide my CF4 up like this, I got 2 fluorines pulling that way, 2 fluorines pulling that way. That's equal. But here, if I slice it along that plane, I got fluorines pulling down and to the left, and hydrogens pulling up and to the right. Those do not balance, because F and H are not the same thing. So this one is polar. And the strongest intermolecular force is dipole-dipole forces. I know it's not hydrogen bonding because the hydrogens are not connected to nitrogen, oxygen, or fluorine. That's it. All of these were tetrahedral. I wonder if we're going to get anything new for number 4. Well, it's CH3F, so the answer is no. I'm going to draw my carbon, my hydrogen, I'm going to draw a fluorine here, a fluorine there, and a fluorine there. All my fluorines need lone pairs on the Lewis structure. These are probably looking pretty similar to the ones we did just before. There are 4 things connected to carbon, so it's AX4. It is tetrahedral again. Here we are. So I'm going to draw my 3D structure the same way I always draw it for tetrahedral. 2 things in the plane of the page, H and F. My other 2 F's, one coming at you, one going away. Now again, if I slice it along this plane, I've got 2 fluorines pulling down to the left and only 1 fluorine pulling up and to the right. Those do not cancel because it's not the same thing on both sides. So, is it polar? Yes. And what's the strongest intermolecular force? Again, because we're dealing with polar molecules, it is dipole-dipole. Last one, that's tetrahedral. It's the last example. Are you bored yet? This one, oh man, I drew the wrong one in the wrong place. Did you guys catch me doing that? Doesn't matter to me. This looks exactly the same. I'm just gonna, have these be switched. It's gonna look exactly the same as you expect. I got H, H, and H. I'm gonna have to, oops, that one's going into the page. There's my F. It's AX4 again. It's tetrahedral again. I hope you guys are as bored with this example as I am. Is it polar? Yes, it is polar for the same reason, because 2 H's don't cancel with an H and an F. And so the strongest intermolecular force is dipole. Dipole again. Again, I botched this. I'm going to have to be very careful about how I read these things. What? CH3. This is CF3. This is CH3F. There you go. Got it. There you go. O3 is at least a little more interesting. I'm going to draw the Lewis structure of this one very carefully for you, right in front of you. Each oxygen brings 6 electrons. That makes 18 total. I'm going to put 1 oxygen in the center and 1 on either side. I draw my bonding pairs in between the 2. Then I draw lone pairs on the outer atoms, until they have a full octet. And I've currently put 16 electrons down. All the extra electrons, I need 18 total, go onto the central atom, and here we are. Now, you might notice that this oxygen doesn't have a complete octet. I'm going to move 1 bonding pair of electrons into it to give it a double bond, and that is one of the valid Lewis structures. The other valid Lewis structure is the exact reverse of it. For those of you in the know, you may recognize that we have some resonance here. But in both cases, the central oxygen, A, is connected to 2 atoms, X2, and has 1 lone pair, E. You can put E1 if you want, I don't. AX2E is a bent shape. You can also call it non-linear or V-shaped. I've found some teachers are very specific. Some will say that AX2E is specifically V-shape, and then some other one, I think it's AX2E2 is non-linear. Just be careful about which one your teacher wants here. I see all 3 of these used interchangeably in the real world though, so I'm putting them down for you. All of the bonds here are between oxygen and oxygen, so by definition they are non-polar. The geometry does not even matter. O3 would never be polar. And so the strongest intermolecular forces is LDFs. If I draw my oxygen in the center here, 1 oxygen goes here and another oxygen goes here. I'm going to make that one the double bond because I can. And the lone pair goes up here. There's only 3 things here. They differ by about 120 degrees because this comes from trigonal planar. You can kind of imagine these electrons taking up the same space as if there was another oxygen there. And so the bond angles are about 120. This actually ends up being 118, 117, something like that. But it can sit in the plane of the page just like these two pens are sitting flat against the page. Back here for tetrahedral, there's no way you can force all four of these substituents to sit flat against the page. We could get two of them to sit against the page, but the other two came out at you and went back into the page. NH3. Nitrogen brings 5 electrons and hydrogen brings 3 each. That's 8 total. So 1, 2, 3 hydrogens, which require 6 bonding electrons total. I have 2 extra electrons because, again, we brought 8 total. So we put a lone pair on that central nitrogen. Beautiful. That central atom has 3 atoms on it and 1 lone pair. It is called AX3E, and by definition, AX3E is called trigonal pyramidal. Trigonal pyramidal. You can call it pyramidal or pyramidal. No one's going to sue you. If I had to draw this in 3D, which I am being asked to do, I draw it just like it was tetrahedral. I draw one of my substituents flat against the page, I draw one coming out at us, and I draw one going back into the page. There's a lone pair up here. I love putting the lone pair at the top so that I preserve the tripod that's always present for tetrahedral molecules. This emphasizes to people that it looks very similar to tetrahedral, except you don't have that one atom, that extra atom sticking out the top, like you do when there are 4 substituents. Cool? Trigonal pyramidal and tetrahedral are very closely related. What I mean is tetrahedral has a bond angle of 109.5 and trigonal pyramidal is about 107, just a little less than the 109.5 because these 3 things get pushed slightly closer together because the lone pair is repelling them. Anyways, this nitrogen is bonded to the H's, and there is nothing to balance it out above the nitrogen. All these, I want to say that the N is pulling up on these 3 hydrogens, but it's not pulling down on anything. It's imbalanced. I can guarantee you that just with the symmetry of it. There's 3 things below it, but not above it. It is a polar molecule, and because you have hydrogen directly connected to a nitrogen, the strongest molecular force in this case is hydrogen bonding. Now make no mistake, there are still dipole-dipole forces in a sample of ammonia, and there are London dispersion forces, but the strongest intermolecular force here is hydrogen bonding. Let's do it for NH2Br. This is going to be very similar, except you have a bromine, which brings 7 electrons with it, 2 hydrogens, and there's the lone pair you need for nitrogen. I'm going to draw this for you. I'm going to draw it the exact same way I just drew the last one. Nitrogen, hydrogen, hydrogen. I'm going to put my bromine here. The Vesper notation is the exact same because you have 3 atoms and 1 lone pair. The molecular shape is the same. I'm going to call it trig here because I don't feel like writing that out. And again, I could slice it this way and show you that there are 3 atoms below that line and none above, so it's imbalanced. But I can also even slice it this way and say, well, I have 2 hydrogens on this side and 1 bromine on this side. That's clearly not balanced either. So this is polar, yes. And again, I have NH bonds, so my strongest intermolecular force is hydrogen bonding. Yeah? Yeah. And again with this, I wonder if I made this a little too repetitive. Let's take a look. Da 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 da. Lewis structures with the lone pair on nitrogen. Make no mistake, this is basically the exact same thing, except I got bromines where one of the hydrogens went before. There's my lone pairs. There's my hydrogen. Because it's trigonal pyramidal again, I'm just drawing it like it's tetrahedral and putting nothing on top but the lone pair. Another AX3E that is polar because it's imbalanced. We have one Br on each side. That sounds like it might cancel out, but I've got a hydrogen over here that I don't have over here. That causes an imbalance in where the electrons are distributed, so it's polar. And we do have an extra H here, so the strongest intermolecular force is hydrogen bonding again. The last one that is similar is NBr3, and I'm including this for a very specific reason. If you look up the electronegativities of nitrogen and bromine, you will find that they are almost the same. What that means is that the NBr bonds are not polar to start with. You can't add up a bunch of non-polar bonds to get a polar molecule. That's impossible. That's against the definition of polarity. So even though this has the same VSEPR notation, and it seems to be built almost the exact same way as the molecules from the previous page, these bonds are nonpolar and the molecule is nonpolar. And there's no NH bonds, so hydrogen bonding isn't present. It's not polar, so dipole-dipole forces aren't present. The strongest intermolecular force here are London dispersion forces. How's that for a twist at the end? All right, let's do formaldehyde. You got your carbon connected to two hydrogens. Hydrogens are always single bonded. Oxygen brings 6 electrons. Carbon brought 4. What that means is that oxygen and carbon are going to have to share in order for there to be 2 plus 4 plus 6. That's 12 electrons total in the Lewis structure. This molecule has a central atom with 3 substituents, and there are no lone pairs on the carbon. That means the shape is trigonal planar. It is flat. You can distribute 3 things around a center and have them all flush against a page. That's as far apart as these 3 things can get from each other. The bond angles are 120, and the 3D structure doesn't actually need 3 dimensions to be shown. The 3D structure is the exact same thing. It's flat, 120 degrees. Is it polar? Well, yes. The carbon-oxygen bond is not balanced out on the bottom half here. And so the strongest intermolecular force is dipole-dipole. Not a surprise. It's a small molecule, but it is polar. So there are dipole-dipole forces. CO2 is the other one, and I made reference to there not being another oxygen to balance it out on the other side, because here there is. This is a central atom with 2 atoms attached to it and no lone pairs. Even though I haven't mentioned it before, double bonds count the exact same as single bonds when it comes to VSEPR notation. This is a linear molecule, and because it is symmetrical on either side, oxygen on the left, oxygen on the right, it is not a polar molecule, and the strongest intermolecular force is LDFs. Linear molecules can be both flush, like the carbon-oxygen bonds can both be flush against the page, so you don't need 3 dimensions to show this one either. If you're asked to draw a 3D structure for it, just draw the Lewis structure again. Cool, let's do a few more. We got SF2. Let's be careful about this one. S brings 6 electrons each, and fluorine brings 7 each. Adding those together gives me 14, that's 20 electrons total. Oh, I'm doing it off the page. I'm going to put my sulfur down, connected to 2 fluorines. I'm going to fill the octet on my outer atoms. That gives me 16 electrons total, but I need 20. So I have 2 lone pairs on that sulfur. If you've done any VSEPR before, you'll recognize this molecule shape, AX2E2, as the exact same shape as water. It is bent, or sometimes non-linear, or sometimes V-shaped. Again, ask your teacher which one they prefer. The 3D structure here doesn't need 3 dimensions, but you will have to show the 2 fluorine atoms at about 107 109.5 degree angle is where it comes from, but we got two lone pairs, so it pushes the fluorines slightly more together. And you can draw your lone pairs in there. This is just like tetrahedral, although we only have two atoms as substituents, so those two can be the two that we choose to have flush against the page. Not really any 3D structure to this at all. Is it polar? Well, sulfur-fluorine bonds are polar, and when drawn this way, it's clear that both the fluorines are pulling down and there's nothing pulling up to balance them out. So yes, it is polar, and the strongest intermolecular force are dipole-dipole forces. SF4 is similar. We've got a sulfur connected to 4 fluorines. I think I should count my electrons again. Sulfur brings 6, fluorine brings 7 each, and there are 4 of them. That makes 34 electrons total. Once I put my fluorines down and fill their octets, I will have 32 electrons, which means I have 2 extra, so I dump them on the central atom. This is the first time we have a violation of the octet rule on the central atom. Anything from phosphorus onwards, to the right or below, can violate the octet rule, and sulfur is the first example we're seeing right here, right now. You have the central atom with 4 substituents as atoms and 1 lone pair. It comes from trigonal bipyramidal, but one of the F's has been ripped off. One of the atoms has been ripped off, replaced with a lone pair, and you end up with a shape that lots of people end up calling seesaw, others call sawhorse. The way I like drawing that personally is to draw 2 atoms 180 degrees from each other, and then I draw one coming out at you and one going into the page. I put my lone pair up here. The reason it's called seesaw is because you can kind of picture these 2 atoms as a teeter-totter or whatever, like the base of a teeter-totter, and then it goes back and forth and back and forth. Anyways, it's just called seesaw. Is it polar? Yes, especially when you draw it this way, you see that there are no fluorines balancing it in the upward direction, and so the strongest intermolecular force is also dipole-dipole. There we go. SF6, central sulfur, 6 fluorines surrounding it, F, 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 F. There are no lone pairs on the sulfur. That's because each fluorine brought 7 and sulfur brought 6. Each fluorine needs just 1 extra electron, and the sulfur brought 1 electron for each of the fluorines. This VSEPR notation is AX6 because there are 6 atoms connected to the sulfur and no lone pairs. That molecule shape is called octahedral. I know it's weird that 6 substituents is called octahedral, but it's because the shape that this makes has 8 faces to it. Is it polar? It is not. And in the Lewis structure, you can kind of see that no matter how I'm cutting it, there's always 3 fluorines on either side. The 3D structure may convince you of that. I like drawing my square of fluorines here, and then showing 1 fluorine coming out at us, and 1 fluorine going back into the page. It's kind of like each fluorine represents one, like the X, Y, and Z axes, if you're into, the math that has 3 dimensions to it. X-axis, Y-axis, Z-axis. You can probably see it. If you can't, just trust me, everything's at 90 degrees to each other. The strongest intermolecular force here, because it's not polar, is London dispersion forces. The London dispersion forces are very strong because it's a heavy molecule, but it's London dispersion forces nonetheless. What are we being asked to draw here? Looks like PF3. Phosphorus brings 5 electrons. It will share 1 with each of the fluorines. Fluorine now has a complete octet for each, and that phosphorus has 2 extra electrons left over. Here we are. This reminds me of NH3 because it's the exact same Vesper notation and molecule shape. Do you remember what we called it? We called it trigonal pyramidal. Is it polar? Well, yes, because phosphorus-fluorine bonds are polar. And if we draw the 3D structure, you'll see that all of the fluorines are pulling down from one particular vantage point, just like all of the hydrogens were on one side of the plane in NH3. This one does not have hydrogen at all, so there cannot be hydrogen bonding. The strongest intermolecular force here is dipole-dipole. Cool? Cool. Let's do PF5 together. Here, phosphorus shares 1 electron with each of the fluorines and has none left over for a lone pair. It's just phosphorus and 5 fluorines with full octets. That's AX5. I like this one. It's called trigonal bipyramidal because there is like 3 of these fluorines make a trigonal planar base, but then there's a fluorine sticking out above and below it. I'm going to draw it exactly like that to emphasize it to you. There is a fluorine. Here's the fluorine coming out at you, and here's the fluorine going into the page. Looking at that, you can probably see why it's called trigonal pyramidal. Trigonal at all. And then the pyramidal, it comes from this fluorine making a pyramid in the upward direction, and this fluorine making a pyramid in the downward direction. It's pretty sweet. Is it polar? Well, from every way you slice this, 2 fluorines here, this one might be a little misleading to slice it this way. It looks like it's 2 and 1, but because of the angles these are on, they actually cancel perfectly with that 1F there. Long story short, it's symmetrical in all directions. Is it polar? No. So the strongest intermolecular force are LDFs. Iodine monofluoride. Iodine brings 7 electrons and fluorine brings 7 electrons. If you know what F2 or Cl2 or Br2 or I2 look like, this looks exactly the same. I can't even tell which of these is the central atom. I would maybe call this Vesper notation AX1, but I would also argue there isn't even a central atom to worry about. If you only have 2 atoms connected to each other, we just call it linear and leave it at that. It's linear so it can sit flat. There's no actual 3D structure to this. Is it polar? Well, I and F have different electronegativities, so yes. And the strongest intermolecular force here is dipole-dipole. Yeah? Yeah. We're going to ramp this up, though, and add some extra fluorines. I'm just readjusting where I'm sitting here. Again, iodine brings 7 electrons, and each fluorine brings 7 electrons. That makes 28 total. I'm going to put my I here. I'm going to put down my fluorines, fill their octets, and once I do, that's going to be 24 electrons total. I need 28, so I need 2 lone pairs on this I. This is AX3 for 3 atoms, and E2 for 2 lone pairs. Now I want to point out that this shape is going to have come from this shape, trigonal bipyramidal. The only difference is that 2 of the fluorines have been ripped off and replaced with lone pairs. And you can kind of see the shape that's remaining there looks like a T. A T on its side, but a T nonetheless. And it might be no surprise to you that a T can sit flush against the plane of the page. Thus, there's no actual 3D structure to show. And finally, it probably doesn't surprise you that a T-shaped molecule is called T-shaped. I like this one because I like the letter T. Is it polar? Well, yes, especially if I slice it this way. You can see that this one fluorine does not have anything on the other side to balance it out at all. And so the strongest intermolecular force here is dipole-dipole. Yes. I'm going to switch colors. I'm doing IF5. Pretty similar again. Iodine brings 7, each fluorine brings 7. That makes for 42 electrons. If I put my I down and surround it with fluorines, 5 of them, that's going to give me 40 electrons total. I can't believe I'm spending my time drawing all these lone pairs for you. That's 40 electrons. 8 plus 8 plus 8 plus 8 plus 8. And I need 42, so I have one lone pair shown here. This AX5E comes from octahedral. What would you get if you took the octahedral molecule that we've already seen together, SF6, and just chopped one of the fluorines off? Well, you'd be left with this pyramid, and there are 4 fluorines making the base of the pyramid. This is called square pyramidal. That's probably going to remind you of trigonal pyramidal or trigonal bipyramidal, because I have an iodine with 4 fluorines as the base. And then I have 1 fluorine either coming up above or below. I like doing it above because then it looks like one of the pyramids from Egypt. And there's my 3D structure. Is it polar? Yes, the F on top here has nothing below the I to cancel it out. And so the strongest intermolecular force is dipole-dipole. Yes, yes it is. Lastly, for this page, we have a charged molecule, IF4, with a minus charge. Each iodine, one of them, brings 7 electrons. We have 4 fluorines, they bring 7 each. And because there's a minus charge, we have to add 1 extra electron. That gives us 28, 29, 36 electrons total. I hope I counted right. I, with 4 fluorines, gives me 32 electrons total. If you're wondering how I'm doing that so fast, I'm just taking the 4 atoms that have full octets and multiplying that by 8. It's 32 electrons. Now I need 36, so I need to dump 2 lone pairs on the central atom, and this ends up as AX4E2. There are still 6 things total connected to the A, so this comes from octahedral as well. This is the same as this, except you're missing 1 more fluorine. So I draw my I here, and I'm actually just going to draw the F's in a square around it. No 3D structure needed. One thing I do want to point out that I've actually forgotten right here is that most teachers want you to put Lewis structures of charged atoms in square brackets with the charge on the outside. This is called square as well because these 4 fluorines are still in a square, but planar because it can sit flat. The fluorine that was below the square is gone, and the fluorine that was above the square is gone, at least relative to octahedral. Is it polar? The answer is no, because no matter which way you slice this shape, it actually ends up canceling out. This fluorine clearly cancels out this fluorine. They're pulling in opposite directions. And this fluorine cancels with this one because they pull in opposite directions. The strongest intermolecular force here are LDFs. XeF2. Xe, xenon, is a noble gas and so brings 8 electrons each. And the fluorine, a halogen, brings 7 electrons each. When you add 14 and 8, you end up with 22. So let's put our xenon in the center, and we'll put a fluorine on either side. We fill the octets of fluorine, and we end up with 16 electrons total so far. We need 22. 18, 20, 22. That's 3 lone pairs on the xenon. That is A for the central atom, X2 for the 2 atoms, and E3 for the 3 lone pairs. Now, that's 5 things total, so this comes from trigonal bipyramidal, and the 3 lone pairs take the places of the 3 things that actually form the trigonal part of the trigonal bipyramid. This ends up being just linear. Is it polar? Well, it's linear and you have fluorine on both sides, so they cancel each other out, and no, it is not. In fact, the strongest intermolecular force here is London dispersion forces. It's a completely flat molecule, so there's no 3D shape to speak of. Let's do XEF4. This xenon has 4 fluorines around it. Xenon brings 8 and fluorine brings 7 each. That makes 36. When we add all the electrons on the outer parts of fluorine, we end up with 32. So we dump 2 lone pairs on the central atom, and now xenon has 2 lone pairs and 5 atoms around it. That makes it AX4E2. By definition, AX4E2 is square planar. We've already seen it before, but it's octahedral without the top and bottom atoms. Is it polar? No, because it is perfectly symmetrical. These 2 fluorines cancel out and these 2 fluorines cancel out. And so the strongest intermolecular force here is also LDFs. Because it is planar, it sits flat against the page and there's no 3D structure here either. Okay, BeI2. Beryllium is one of the exceptions to the octet rule in the it doesn't quite need 8 direction. In fact, beryllium is perfectly happy with just 4 electrons. It brought 2, and each iodine brought 7, so they share to make a covalent bond, and this is it. Even though beryllium doesn't have the full octet, this is the Lewis structure. This is AX2, just 2 atoms. AX2, like carbon dioxide, is linear, and because they are the same atom on either side of the beryllium, it is not polar either. LDFs here as well. I can't remember if BeI2 is actually ionic, but in the gas phase, I believe it forms a molecule like this. Again, because it is linear, you can lay it flat against the page and there's no 3D structure there either. Cool. What are we doing now? BH3. Well, boron is one of the exceptions as well. It's perfectly happy with just 6 electrons around it, and this is it. That's your Lewis structure. It's AX3, which is trigonal planar, and again with the planar, it just sits flush against the page. Nothing has to stick up or out of the page, and so there's no 3D structure to speak of. These are symmetrically distributed, so it is not polar. And if this molecule is in the gas phase, there's no stronger intermolecular force than the London dispersion forces. There's no dipole-dipole or hydrogen bonding. AlCl3 is a little weird. AlCl3 is often written like this in isolation. Aluminum is in the same group as boron, so can handle just 6 valence electrons like that. But the actual structure has the Al accepting an extra lone pair from a chlorine, and they actually take on a tetrahedral structure. Can you see here we have an AlCl3 that's actually covalent bonded, and over here we have another AlCl3 that's actually also covalent bonded. In fact, if I was to give you 3D structure, I might say one of them is going out of the page and one of them's coming into the page. This is Al2Cl6, which is the solid form of AlCl3. In this case, it's trigonal planar, and in this case, it's actually tetrahedral around each aluminum. Whichever one of these your teacher actually cares about tells you which one. Like, does your teacher actually expect you to know that it's Al2Cl6? Probably not until university, at least here in Ontario. But it's either going to be AX3 or AX4. That's trigonal planar or tetrahedral. In both cases, you have a non-polar molecule. No, it is not polar because all of the chlorines are symmetrically distributed here. And so the strongest intermolecular force is a London dispersion force. I'm oversimplifying these attractions. These are dative bonds made between the molecules. And it's technically an intermolecular force, but it's strong enough that we can actually call it a molecule. I'm just going to say it's LDFs because I expect that's what your teacher wants. The carbon in diamond, I just want to take this opportunity to tell you that the carbon in diamond is tetrahedral. Each carbon is surrounded by 4 other carbons, and it goes on like that in all directions. It's just like methane's, except all the H's are carbons, and all the H's on those are also carbons. And it goes on and on and on. It is AX4, and it is tetrahedral. Now, there's no actual molecule here. One piece of diamond is one large network of carbon atoms. It's technically one molecule because it's covalent bonds throughout. And it is certainly not polar because all of the bonds between carbon and carbon have an electronegativity difference of 0 because they're both carbons. Cool? Excuse me. Cool. You might also have been required to know what the structure of SiO2 is. Each silicon is connected to 4 oxygens, and each oxygen is connected to just 2 silicons. So, the VSEPR notation depends on which one you're talking about. The silicon is AX4, and the oxygen is AX2E2. We're talking about the silicon specifically, but I will give you both because I've already started. AX4 is tetrahedral. Yes, it is. And AX2E2 is linear, V-shaped, or bent. I'm going to be lazy and just write bent here. Is SiO2 polar? Well, that's a tough question. These silicons are surrounded symmetrically by all of the oxygens, but the oxygens are connected to 2 silicons in a non-symmetrical way because of where the 2 lone pairs are. So the around each oxygen, you actually end up with what looks to be a polar molecule, but then again, the whole SiO2 structure, which repeats over and over and over again, is one big molecule. So technically SiO2 isn't polar, but whatever. And there's no intermolecular forces because SiO2 is a large molecule. Okay, let's get back to molecules. Each nitrogen brings 5 electrons, and we add 1 for the minus charge. This is actually the azide anion, and it's one of my favorites. We're going to do 3 N's in a row, 1, 2, 3. Bonding pairs, we're going to fill the octets of the outer atoms. Oh, and we are done. Now this nitrogen doesn't have a full octet, and nitrogen needs a full octet. So we're going to move 1 lone pair here, and another lone pair here. The final Lewis structure is the middle N double bonded to either of the end ends. We like putting it in square brackets with a minus charge. The middle nitrogen here is surrounded by 2 other atoms, which makes it AX2 and linear. It is certainly not polar because they're all nitrogen atoms, so there are no polar bonds, and therefore within, like, if N3 minuses could interact with each other, they would be LDFs, but I wouldn't count on that because N3 is only present in ionic compounds anyways. Because it's linear, there is no 3D structure to show, and we just leave her there. NO3 minus. Okay, the oxy anions are important enough to talk about on their own. The problem with oxy anions is resonance. In nitrate, for example, one of the oxygens is double bonded in the Lewis structure, but realistically what's actually happening is that each of the bonds represents a 1 1/3 bond. There are resonance structures that have this oxygen double bonded and this oxygen double bonded, and they all contribute equally to make a resonance structure where all the NO bonds are about 1 1/3. In any case, in both of these structures, most specifically the resonance hybrid, there is a central atom surrounded by 3 oxygens with no lone pairs. Don't forget your square brackets with your minus charge. The molecule shape is trigonal planar because there are no lone pairs and there are 3 atoms. Is it polar? No, because the oxygens are evenly distributed. And if nitrates could interact with other nitrates, it would end up being LDFs as well. Most of the time you have HNO3 or something else bonded to the nitrate. we're going to talk about ClO2-, I think it's the chlorite anion. Chlorine brings 7, oxygen brings 6 each, and we add 1 for the minus charge. This gives us 12, 19, 20 total. Give me that chlorine, an oxygen on either side. I'm going to complete the octet on these oxygens, and I'm going to dump extra electrons on the chlorine. Now, to finalize the formal charge here, to finalize the Lewis structure, we need to consider formal charge. Chlorine brought 7 electrons. It currently has 2 bonds and 2 lone pairs, which represent 4 electrons that belong to the chlorine itself. That gives it a formal charge of +1. The formal charge on these oxygens, as it currently stands, is -1 each. We can alleviate that formal charge by moving one of these lone pairs into the double bond. But from which one does it come? The answer to that is it comes, it's contributed equally by both. So we have each of these oxygens bonded 1.5 times, or a 1.5 equivalent covalent bond, with 2 lone pairs. The number, the bond order here, doesn't actually matter. What matters is that you have 2 electrons and 2 lone pairs. I wanted to draw the proper Lewis structure for you because I asked for it, though. Even from the wrong Lewis structure here, just counting the electrons properly, you can see that it is an AX2E2 shape. That is bent or linear or V-shaped. Bent or non-linear or V-shaped. Is it polar? Well, in isolation, yes, because oh no, it is not, because chlorine-oxygen bonds are not polar. They're close enough in electronegativity that you don't have to worry about it. And the strongest intermolecular force among non-polar molecules is always LDFs. Now I want to emphasize that the resonance did not actually affect the VSEPR shape here. Chlorine brings 7, oxygen brings 6 each, and we add 1 for the minus charge. That gives us 26. Chlorine bonded to 3 oxygens gives us 28 electrons total. And, 24 electrons total. So we dump the extra 2 to make 26 on the central chlorine. Now, whether or not these oxygens contribute to make double bonds or not actually is irrelevant to the VSEPR shape. This is still AX3E, and therefore trigonal pyramidal. It is going to be polar if it was in isolation. Oh no, it's not. I made the same mistake because chlorine and oxygen have electronegativities. They're close to each other. And so therefore it's LDF. Man, I wanted that to be polar, but it's not. I believe that what you actually have here is chlorine on average bonded 1.66 times to each oxygen, kind of like this, where 2 oxygens are double bonded at any one time for each of the resonance structures. That's neither here nor there, though. And this perchlorate has 4 oxygens. I wonder if there's any lone pairs. Well, 7 electrons for the chlorine, 4 times 6 for the oxygens, plus 1 gives me 32. Nope. 4 oxygens with full octets would make this satisfied with, it's mine, let me say that again. This is all the electrons because we only need 32 electrons total. One of the resonance structures here has 3 double bonded oxygens, but which 3 is it? Well, it varies. And so there's a resonance hybrid where the average bond order is 1.75. Again, that's neither here nor there because the VSEPR shape of both of these is AX4. There are no lone pairs. That means it is tetrahedral. And tetrahedral things, as long as all the things around it are the same, is not polar. These bonds aren't polar, so it's not polar for that reason too. And so LDF would be the primary intermolecular force there. Whew. We're in the home stretch. These are the last 3 in the booklet I have here. CO carbon brings 4 electrons and oxygen brings 6. That makes 10. I'm going to bond them twice, with 2 electrons. 2, 4, that's 8 electrons total. That's 10. But carbon doesn't have a full octet, so I'm going to take one of those lone pairs and put it there. I'm going to take this lone pair and put it there. This is a triple bond, but there's only 2 atoms here. I wouldn't give a Vesper notation for this. I guess you could call it AX, and that's it. But if there's only 2 atoms, we call it linear. Is it polar? Yes, it is, because carbon and oxygen have differing electronegativities. And so the strongest intermolecular force here is dipole-dipole. Yes. HCN. H brings 1, carbon brings 4, nitrogen brings 5. That makes 10 total. HCN, 2, 4 electrons, 6, 8, 10. That's it. Although carbon doesn't have a full octet. So we'll move that lone pair in here, we'll move that lone pair in here, and now we have the Dunn-Lewis structure. The Vesper notation for carbon here is AX2 because it's surrounded by 2 atoms and has no lone pairs. It is linear, thus has no 3D structure to it. Is it polar? Yes, because nitrogen and hydrogen have different electronegativities, so they don't cancel each other out. And so dipole-dipole forces are the strongest IMF here as well. Last one, OF2. Oxygen bonded to 2 fluorines. Oxygen brings 6, fluorine brings 7 each. That gives us 20. Filling the octet of the fluorines gives us 16, 17, 18, 19, 20. I have an AX2E2 here, just like water, linear, sorry, I did it again, non-linear, V-shaped or bent. Is it polar? Yes, because these 2 fluorines pull downward relative to this oxygen, and there's nothing to counteract it in the upward direction. So the strongest IMF is dipole-dipole here as well. But also, because this comes from tetrahedral and you're allowed to have 2 things flush to the page in tetrahedral, this is it. There's no 3D structure. Oh man, when was the last time we saw any 3D structure? I guess it would have been ClO4-. We would have had to draw 1 oxygen up, 1 oxygen this way, 1 oxygen coming at you, 1 oxygen going into the page, big minus charge. And for trigonal pyramidal, remember I like to copy what I do for tetrahedral, except I put the lone pair on top, just like that. That's a chlorine. I gotta give the minus charge for that. And for bent, there's no reason to show any of that. This is the exact same as OF2, isn't it? I'm being lazy about showing my resonance here because that's almost an hour of Vesper that you've been doing with me. Thanks for staying with me. You're a good person. Best of luck.